Let's solve some previous year gate problems from the topic brakes, springs and gears. A disc clutch with a single friction surface, single friction surface has a coefficient of friction mu is equal to 0.3. The maximum pressure which can be imposed on the friction material is 1.5 megapascal. So this is the maximum pressure that can be imposed on the friction material. The outer diameter of the clutch plate is 200 mm. Be careful, this is the outer diameter, and in our uniform pressure theory and uniform wear theories, in the formulas we generally consider radius. So the outer diameter of the clutch is 200 mm, that is outer radius capital R is 100 mm, that is 0.1 meter, and its internal diameter is 100 mm, that is small r is 50 mm, that is 0.05 meter. Okay, assuming uniform wear theory for the clutch plate, the maximum torque that can be transmitted is, okay, so the torque that can be transmitted is given by the equation N mu W R mean. Okay, so N is the friction number of friction surfaces, which in this case is 1, so N is 1. Mu is the coefficient of friction, which is equal to 0.3. W, we don't know. W is the load that can be imposed on the friction material, and R mean is the mean radius that is used in case of uniform wear theory, which is outer radius plus inner radius upon 2. Okay, now this is 0.075 meters. So now we have to find W, and if we find W, we can find out the maximum torque that can be transmitted. So you have been given the maximum pressure that can be imposed on the friction material. So according to UWT, that is uniform wear theory, maximum pressure is equal to load upon 2 pi r, small r, okay, because on internal diameter there will be maximum pressure, so 2 pi r capital R minus r. Okay, so this is a maximum pressure, and maximum pressure is 1.5 megapascal, that is 1.5 into 10 raised to power 6 pascal into 2 pi small r is 0.05 meter, and the difference is again 0.05 meter is equal to load W. So solve it. W will be 23561.9449 Newton. Okay, put this value of load which can be imposed on the friction material in this formula, and you will get the value of torque will be, and that will be equal to 530.143 Newton meter. Okay, so directly based on the formulas, this question was directly based on the formulas. Okay, be careful that which theory has been given, okay, because sometimes I have seen students committing mistake that uniform wear theory is given and they use uniform pressure theory. So uniform wear theory is given. Okay, and also be careful that the value of diameters were given in the question, but in the formulas we use radius. Okay, so, next question. A drum brake is shown in the figure. The drum is rotating in anti-clockwise direction. Okay, the coefficient of friction between drum and shoe is 0.2, that is mu is 0.2, and the dimensions are given in the figure, and they are in mm. Okay, the braking torque in Newton meter. Take care of the units that you have to find the braking torque in Newton meter for the brake shoe is. Okay, so for this brake shoe, the braking torque is equal to friction force into radius of the drum. Okay, so this is what we have to find. So we have the radius of the drum, that is 0.2 meter. This is 200 mm, so 0.2 meter is the radius of the drum, and we have to find the friction force that is actually applied by this pad on the drum. Okay, and the friction force is actually equal to mu n, that is coefficient of friction into normal reaction. Okay, So if we multiply both of them, we'll get the braking torque. Okay, draw the FBD of the lever and this braking pad and the drum. Okay, so so this is rotating in anti-clockwise direction. Okay, and if I press the brake, so there will be the normal reaction exerted by this pad on the drum in the downward direction, which is N, and this this pad, braking pad, will try to stop its rotation. So that implies it will be exerting a friction force in the opposite direction of the rotation of the drum. Okay, so this is the friction force. Okay, and similarly, if you draw the FBD of the lever with this braking pad, okay, let me draw it clearly. Okay, so similarly there will be a normal reaction in the upward direction. Okay, and on the drum, if the friction force is in the right hand side direction, on this braking pad it will be in the left hand side direction. Okay, and there's a force that is acting here and whose value is equal to 1000 Newton. So this is the FBD of the lever and the drum. Okay, now you have to find the value of N. If you get the value of N, you will get the value of friction force and ultimately the torque. Okay, so about this hinge, you can write the moment equation by all these forces. Okay, so let us take the clockwise direction. The moment in the clockwise direction is positive, so 1000 into this distance, this is given as 800 mm. Okay, so this is 800 mm, so 1000 into 800 mm, but in anti-clockwise direction, so this will be with a negative sign, minus 1000 into 800 plus the friction force, and this distance is 100 mm. So friction force about this hinge will be creating a moment in the clockwise direction, so that is plus F into 100, and there is one more force, that is normal reaction. So the normal reaction about this hinge will also be creating the moment in this direction, the clockwise direction, so plus N into this distance is 480 mm. Okay, is equal to 0. No need to convert these distances in meter, because you can take the factor common, and on the right hand side we have equated the equation to 0. Okay, so solve it. Put this F equal to mu N, and mu is equal to 0.2. Okay, yeah, so there is only one variable, that is normal reaction in this equation. You solve it, N will be equal to 1600 Newton. Okay, this is what you have wanted. So mu is equal to 0.2 into 1600 into 0.2 again, that is the radius of the drum, and torque is equal to 64 Newton meter. Okay, so the braking torque in Newton meter for the brake shoe is 64 Newton meter. Okay, next question. The forces F1 and F2 in a brake band, and the direction of rotation of the drum are as shown in the figure. The coefficient of friction mu is given, that is 0.25, and the angle of wrap is given, that is theta is given in radians. Theta is 3 pi by 2. So in the formula of band brake, you actually put the theta in radians, and here in the question the theta is given in radians only. Okay, it is given that R is equal to 1 meter, that is radius of the drum is 1 meter, and F2 is 1 Newton. Okay, the torque in Newton meter exerted on the drum is, okay, so that is you have to find the braking torque again, and in a band brake, the braking torque is equal to F1 minus F2 to R. That is the difference between the tensions into the radius of the drum. Okay, so we know F2, that is 1 Newton. We know the radius of the drum, but we don't know F1. And F1 by F2 we can find out by this relation, which can be used in a band brake, that is F1 by F2. That is the ratio of these tensions is equal to e raised to the power mu theta. Okay, so e raised to power mu is 0.25 and theta must be in radians. Here in the question the theta is in radians, so that is 3 pi by 2. Okay, so you solve it. F1 will be equal to 3.248 F2, or you can say F1 by F2. The ratio of these tensions is equal to 3.248. Okay, so F2 is 1 Newton, so that implies F1 is equal to 3.248 Newton. Okay, put this F1, F2 and R in this equation number 1 and you will get the braking torque in a Newton meter. That is 3.248 minus 1 into radius of the drum is 1 meter. Okay, so the answer will be 2.248 Newton meter. That is the torque exerted on the drum. Okay, that is 2.248. Okay, next question. Okay, the next question is for the brake shown in the figure, which one of the following is true? Okay, self-energizing for clockwise rotation, self-energizing for anti-clockwise rotation. Okay, so you have to find whether the brake is self-energizing for which rotation of the drum. Okay, so let me tell you that a brake is said to be self-energizing brake when movement due to friction act in the same direction as movement due to effort. Okay, so when you draw the FBD of the lever and this brake drum, this is brake drum, so if the movement due to friction is acting in the same direction as the movement due to effort F, this is effort. Okay, the brake is said to be self-energizing brake. Okay, so let's see whether it is for clockwise rotation of or anti-clockwise rotation of the drum. Okay, so let's assume that the brake drum is rotating in the clockwise direction first of all. So this is our brake drum. It's a bit difficult to draw proper circle on yeah, so the clockwise rotation of the drum, and this is the brake shoe. So the brake shoe will actually try to stop this rotation of the brake drum and hence will apply the friction force in the backward direction. Okay, okay, and similarly there will be a normal reaction that will be exerted by the brake shoe, and for lever about this hinged point, okay, there will be a normal reaction in the upward direction on the shoe, and the friction will be in the opposite direction of that of the brake drum, that is it will be in the forward direction, and this is the effort. Okay, F. So I have told you that for the self-energizing brake, the movement due to this effort should be in the same direction as the movement due to friction. Okay, this hinged point is somewhat here. Yeah, okay, so this is the distance between the brake shoe where the friction force is acting. So the moment due to friction about this hinge is in clockwise direction, and due to effort also it is in the clockwise direction. So I can say that for the clockwise rotation of the drum, the brake will be self-energizing, that is option A. Okay, so the basic main point was the brake is said to be self-energizing when the movement due to friction act in the same direction as the movement due to effort. Okay, next question. A mass of 2000 kg is currently being lowered at a velocity of 2 meter per second from the drum as shown in the figure. The mass moment of inertia of the drum is given. On applying the brake, the mass is brought to rest in a distance of 0.5 meter. Okay, the energy absorbed by the brake in kilojoule. This is more of an engineering mechanics question. So the energy absorbed by the drum, energy absorbed by the drum, by the brake drum, will actually be equal to the change in kinetic energy of the block, because this is being lowered at 2 meter per second, and finally the velocity of the block will be 0. So that is delta ke of block. Okay, plus it is lowered, so that implies its potential energy is also changing, so that is change in potential energy of block. Plus there is one more component, because this drum is also rotating. Okay, so it will be having a kinetic energy, a rotational kinetic energy, so that will be change in rotational kinetic energy of the drum. So all of these energies will be absorbed by the brake drum on applying the brake. Okay, so change in kinetic energy of the block, it will be equal to half m v2 square minus v1 square, but the final velocity will be 0, so half mv square, I'm directly writing it, half m is 2000 kg, and the initial velocity is 2 meter per second, that is 2 square, the final velocity is 0. Okay, change in potential energy of the block. Okay, so by what height the mass is brought to rest? So it is brought to rest in a distance of 0.5 meters. So m is 2000, g is 9.81, h will be 0.5 meters here. Okay, because in this 0.5 meter distance it is brought to rest, so this will be the change, this height will correspond to the change in potential energy of the block. Okay, plus there will be the change in a rotational kinetic energy of the drum, because initially it will be rotating with some omega, and finally this omega will be 0. Okay, so the initial omega we can find out by v is equal to omega r, and v is 2 meter per second, by which the block is being lowered, is equal to omega into r. What is r? R is 1 meter, because the diameter of the drum is 2 meter given here, so the radius will be 1 meter. Omega initial is 2 radian per second, and final omega is 0, so directly I am writing that half I omega square. Okay, I is 150 kilogram meter square, omega square, that is 2 square. Okay, the omega final is 0, so I have not written that term here. Okay, so when you solve it, this will be 4000, this is 4000, plus this will be 9810 plus 300 joule. Okay, so that implies 14110 joule, and you have to find the energy absorbed by the brake in kilojoule. Okay, before filling the answer here, always see whether you have to put the answer in joules or kilojoules or whatever the units. Do confirm the units before putting the value. Okay, so that implies this is 14.11 kilojoule. Okay, so 14.11 kilojoule, this is the answer. Next question is based on uniform pressure theory. This, see here, uniform pressure theory. Okay, a single plate clutch has a friction disc with inner and outer radii. Okay, so single plate clutch is given, that is n is equal to 1, number of friction surfaces is 1, with inner and outer radii. So you have been given the inner and outer radii only directly, that is 0.02 meter is the inner radii, and the outer radius is the 0.04 meter. Okay, the friction lining in the disc is made in such a way that the coefficient of friction mu varies radially, as mu is equal to 0.01 r, where r is in mm. Okay, so now it says that the coefficient of friction is varying, it is not constant. Okay, the clutch needs to transmit a friction torque of 18.85 kilonewton mm. Okay, so that is 18.85 kilonewton mm. Okay, so as per uniform pressure theory, the pressure in megapascal on the disk is, okay, so here the coefficient of friction is actually varying with r, and r is in mm, so we cannot directly use the formula, we'll have to actually integrate it. Okay, so let's start that we know that the torque that can be transmitted is equal to n mu wr. Okay, n mu wr, n is the number of friction surfaces, in this case it is equal to 1. Okay, mu is equal to 0.01 r here. Okay, and w is the load that can be applied on the friction surface, and this can be found out by the relation given by uniform pressure theory, which is equal to which states that pressure is equal to w upon, or you can directly write the load will be equal to pressure into area, and area in this case will be equal to, see, this is the single plate, this is the clutch. Okay, and at a distance r, at a distance r, at a distance r, this thickness is dr. Okay, so the area that will be actually exposed to this load will be equal to 2 pi r into dr. Okay, this will be the area that will be exposed to this load, so this load will be equal to pressure into 2 pi r dr, and this is again r, which is varying. Okay, fuck यार, ये दोबारा कराना पड़ेगा, मजा नहीं आया. कहाँ तक है, 22 मिनट हो भी गए. A single plate clutch has a friction disc with the inner and outer radii of 20 mm and 40 mm respectively. The friction lining in the disc is made in such a way that the coefficient of friction mu varies radially. Okay, so now the coefficient of friction is varying with r, where r is in mm. Okay, the clutch needs to transmit a friction torque of 18.85 kilonewton mm. Check the units. Okay, kilonewton mm. As per uniform pressure theory, the pressure on the disc is, okay, so let's start from our basics only. Okay, do not be confused if you see that the coefficient of friction is also varying. It just says that if the coefficient of friction is varying with radius r, there must be the use of integration somewhere. Okay, so let's start from our basics only. The torque that can be transmitted will be equal to n mu wr. Okay, n in this case is 1 because it is given that a single plate clutch has a friction disk, that is the number of friction surfaces will be 1. Mu is equal to 0.01 r, varying with radius. Okay, and w is the load that can be imposed on the frictional surface of the disc, which is equal to pressure into the area exposed. Okay, pressure into area exposed, and this is r. Okay, what will be the area exposed? Okay, see, at a distance r, I take this small ring dr, so the area exposed to this load will be varying along with r, and the area will be equal to 2 pi r dr. Okay, and therefore the total load equals P into 2 pi r dr. Okay, so on this dr I have actually assumed that on this dr I can actually transmit a torque dt. Okay, so dt is equal to n is 1, that is 0.01, n is 1 and mu is 0.01 r into p into 2 pi r dr into r, small r. Okay, so this is actually the dt torque that can be transmitted by this small thickness dr. Okay, so integrated, so on the left hand side it becomes t, and on the right hand side I will integrate it from r1 to r2. That is, r1 is the inner radii, which is 20 mm, and r2 is the outer radii, which is 40 mm, so that is 20 to 40 mm. Okay, because here the r is in mm. Okay, so 0.01 r p 2 pi r dr r. Okay, so t is 18.85 kilonewton mm, so that will be 18.85 into 10 raised to the power 3 newton mm. So I have kept this the unit here as mm because I have put the value of radius in the right hand side in mm only. Okay, so I will get the pressure in newton per क्या चुतिया पे यार फुद्दू क्वेश्चन है माँ ये है. So on the left hand side, when I integrate it from 0 to t, it becomes torque that is transmitted, and on the right hand side I will integrate it, and from the limits, that is 0.02 meter to 0.04 meter, 0.001 r p 2 pi r dr to r. Okay, so torque is 18.85 kilonewton mm, that is 18.85 newton meter. Okay, I like to work in SI units only. So that is 18.85 newton meter is equal to take this 0.01 out, take this p also out because the uniform pressure theory is given. Okay, so 2 pi comes out of the integration, so this becomes 0.02 to 0.04 r cube dr. Okay, so when you solve it, it will be 18.85 is equal to 0.01 p 2 pi and r4 raised to the r raised to the power 4 by 4, and the limits will be 0.02 meter to 0.04 meter. Okay, so when you solve this, the pressure will be equal to it will be a long term, it will be a long value in newton per meter square. Okay, it will be some long value in newton per meter square, but we have to find the pressure in megapascal, so directly I am writing the answer in megapascal, that is 500.011 megapascal. Okay, because after this is just a calculation part. Okay, like it will be 18.85 is equal to 0.01 p 2 pi, this will be 0.04 raised to the power 4 minus 0.02 raised to the power 4 in brackets upon 4, sorry. Okay, so solve it, you will get the value of pressure that will be equal to 500.011 megapascal. Okay, next question. This question is from springs. If the wire diameter of a compressive helical spring is increased by 2%, the change in spring stiffness. Very basic question. The spring stiffness is given by K is equal to GD raised to the power 4 upon 8D cube N. Okay, this small d is the wire diameter, G is the modulus of rigidity, this is the mean coil diameter of spring, and N is the number of turns. Okay, so keeping everything same, they are just changing the wire diameter by 2%. They are actually increasing the wire diameter. So let this be K1, let this be K2. K2 is G 1.02 of D raised to the power 4 8D cube N. Okay, so the relation between K2 is equal to K1 into 1.02 raised to power 4. Okay, so I can directly write that percent change is equal to 1.024 sorry 1.02 raised to the power 4 K1 minus 1 raised to the power 4 K1 upon 1 raised to the power 4 K1. Okay, so into 100. Okay, percentage change, so the percentage change will be equal to 8.243%. Okay, pretty simple question. Okay, next is it is a question from brakes again. So all you have to do is draw the FBD of the brake drum and the brake lever and shoe, and you will get your answer. Let's read the question. The schematic of the external drum rotating clockwise. The rotation is clockwise, engaging with a shot. The shoe, which should be with a shoe, is shown in the figure. The shoe is mounted at point Y and on a rigid lever XYZ. This lever is rigid XYZ and it is hinged at X. A force F is equal to 100 Newton is applied at the free end. Okay, this is the load that has been applied. This is the effort actually. Given that the coefficient of friction between the shoe, this is a shoe, and the drum is 0.3, the braking torque on the drum is okay. So simple, you have to find the braking torque, that is torque is equal to friction force into radius of drum. Radius of drum is 100 mm, that is 0.1 meter, and friction force is equal to mu n. So you have to find the normal reaction because mu is 0.3 and that is given to you. So if you find the normal reaction, you will get your answer. Okay, so draw the FBD of the brake drum. Okay, this is rotating in clockwise direction, so when the brake is applied, this shoe will exert a normal reaction in the downward direction and a friction force in the backward direction. Okay, I have explained this FBD in the previous questions, and the FBD of the brake shoe and the lever will be there. This is the effort in this direction, this will be the friction force, and normal reaction will be in the upward direction, and this goes somewhat here. Okay, so all you have to do is write the moment equation about this hinged point X, and you will get the normal reaction. Let's write the equation by taking the moment due to a force in anti-clockwise direction is positive. Okay, so this effort F into the distance, what is the distance of this effort from this hinged point is 300 mm. Okay, so F into 300 in anti-clockwise direction. Okay, and the next one is this friction force and this distance is again 300 mm, and this will be in the anti-clockwise direction again, so plus small f into 300, and the moment about the hinged point due to this normal reaction will be in clockwise direction, that is minus n into distance. Perpendicular distance is 200 mm into 200 is equal to 0. Okay, so replace this friction force by mu n. Mu is given to you, that is 0.3. F is also given to you, that is it is 100 Newton. So the only variable is n, that implies 100 into 300 plus 0.3 n into 300 is equal to n into 200. Okay, so n is equal to 272.727 Newton. Put this value here, and the braking torque will be equal to 8.18 Newton meter. Okay, this is the answer. It was the same question. Okay, next is this problem is from gears. Most of the problems from gears we would have covered in TOM only, so this one problem we'll be covering in design. So spur pinion of a pitch diameter 50 mm, the pitch diameter is 50 mm, PCD, rotates at 200 radian per second, omega is 200 radian per second, and transmits 3 kilowatt power. The pressure angle of the tooth of the pinion is 20 degrees, that is phi, is 20 degrees. Okay, assuming that only one pair of the teeth is in contact, great. The total force exerted by a tooth of the pinion on the tooth of a mating gear. Okay, so let me draw a rough tooth of the gear, and on this tooth, this is the normal force or the total force exerted. So this is Fn, this is the radial force, okay, and this is the tangential force, this is Ft. Okay, so this is Fn, Ft. Okay, so this is the tangential force, this is the radial force, and this is the normal force or the total force exerted by the tooth of the pinion on the other tooth. Okay, so we have to find this Fn. Okay, so power is 3 kilowatt, power is equal to T omega, so that is 3000 watt is equal to T is torque, that is we have to find out, and omega is 200 radian per second, so that is 200 radian per second. So torque will be equal to 15 newton meter. Okay, 15 newton meter. Okay, and this torque is equal to tangential force into the radius, the radius of the pinion. Okay, because this tangential force is actually responsible for the rotation of gear, so torque is equal to Ft into R. Okay, so torque is 15, Ft we have to find out, R is 50, R is 25 mm because diameter is 50 mm, so this is 0.025 meters, so that implies Ft is equal to 600 Newton. Okay, so Ft is 600 Newton, and I can find out Fn from here. How? Because this angle is phi, which is 20 degrees, that is, it is the pressure angle which is equal to 20 degrees. So Fn cos phi is equal to Ft. Fn cos phi is equal to Ft. Okay, so Fn is equal to Ft by cos phi, that is by cos 20. So this is 600 by cos 20 Newton. So normal force or the total force exerted by a tooth of a pinion on the tooth of the mating gear is equal to 638.506 Newton. Okay, so before filling the answer, check in which units you have to fill the answer, that is in Newton. So the answer is 638.506.